Hello, my name is Piotr, and together with Jan we have been working on an optimization algorithm in Erlang, and we made efforts to parallelize it and scale it up. So in the next couple of minutes we would like to tell you about the results of our work. First we'll start with the description of the algorithm that we used, its different implementations. We'll present our scaling results and the issues that we encountered during that. And then we'll end up with some conclusions and potential advice. So our algorithm is called EMAS. It means an evolutionary multi-agent system. And it is an intersection of multi-agent systems and evolutionary algorithms. For those of you who are not familiar with multi-agent systems, these are modeling interactions between autonomous beings called agents, which are performing some computation asynchronously. They have their own aims and knowledge, so the data is decentralized and there's no global control. Agents can message each other and can communicate using messages. As for the evolutionary algorithms, this is a general schema of an evolutionary algorithm. It's a class of algorithms which is inspired by phenomena occurring in the nature, and it basically consists of constant reiteration on a population and updates to the population, which composes of the evaluation of fitness of the agents, then selecting some subpopulation of the agents which perform some action, and then putting them back to the pool in some way. As I said, EMAS is an optimization algorithm. It can be used for solving hard problems like scheduling, for example, job shop problem. The autonomous agents represent hypothetical solutions, and the fitness value is how good the solution is in the particular problem. The computation is decentralized, so therefore it is easily parallelizable. And how it works. It's basically a one iteration here, explained. Every red circle is representing an agent, which can choose one of 4 actions: fight, death, migration, reproduction. And a fight involves 2 agents, which compare their fitness values. And the stronger one drains some energy from the weaker one. So it becomes more powerful and can reproduce more often. A death removes an agent from the population pool. A migration moves an agent to another population. And a reproduction takes 2 agents and mixes them, producing some offspring, and then puts them back to the population pool. And EMAS uses a concept of islands, which are independent instances of the same algorithm running on, in different instances, running the same computation but with different data. So agents can also move between these populations using migration. And this concept helps avoiding getting stuck in the local optima and parallelization.
So we managed to develop 4 different implementations of the aforementioned algorithm. All of them share the same basic logic, however they have different architecture, and therefore they scale a little bit differently. So the first one is a sequential version. It does not scale, everything happens in just one process, and we use it mainly as a reference point for all the other implementations. We have a coarse-grained implementation, which we like to call hybrid. In this one, every single island is a separate process, and the islands communicate with each other through message passing. We have a fine-grained implementation, where every single agent is a separate process. And finally, we also have an implementation, also a coarse-grained, but this time using the scale library. I don't think we need to talk a lot about scale because we had already a few presentations about it, but basically it's a tool which enables the programmer to easily parallelize his code without worrying about all the implementation details. And this is the architecture of the coarse-grained versions. So as I said, each island is a separate process. which is completely isolated one from another. Evolution happens in each of those islands separately, and if there is a need for migration, so we need to transfer one agent from an island to another, we use message passing to do this. Although in the Scale implementation we use ETS tables, however it's just an implementation detail. So this is an extract from the scale-based implementations that we have. This is most of the main workflow of our program. So those little skeletons with sec and pipe and feedback atoms, as you can see, these are the patterns that we use. A programmer is expected just to provide a particular function, so I included only the one example function, shuffle one, at the top. So these functions should capture the basic logic behind the program, and then you can put those functions into the skeletons and create more complex structures. So in this example, we have the type variable, and this variable represents one iteration of the program that we have been explaining. And then we put the whole pipe variable, which, as you can see, is quite complex, and we put it into the feedback skeleton, which makes it loop. And then we put it inside the map skeleton, which makes it parallel. And we don't have to worry about spawning processes and all this stuff. And finally, this is the fine-grained implementation that I've been talking about. So here, every single agent is a separate process. And there is no global knowledge in the system. Therefore, we need some way for the agents to communicate and interact with each other. And this is why we introduce arenas. Those rectangles, these are appropriate arenas. So the idea is that when an agent decides to perform a particular action, say he wants to reproduce, he sends a message to the reproduction arena. And the arenas get messages from all the agents from all the virtual machine, from all the agents in a particular island that the arena is at. And they match the agents with each other, and they then perform the interaction. Therefore, agents don't have to know about all the other agents on the island. They just need to know the addresses of the arenas. Okay.
So let's talk about scaling. The testing function that we use is the rastrigging function, which the formula you can see on the slide, and also you can see the graph of the rastrigging function in 2 dimensions. This is multimodal. It has many local optima, so it is hard to optimize, and also good for benchmarking purposes. We used the rastrigging function with 100 dimensions and 64 islands in NMOS. The testing infrastructure was a part of the Academic Computer Center here at the HH University. We used one single node with 64 cores. So there is a belief that if you have an Erlang program and you run it on n cores, it should run n times faster than on a single core, but it's not completely true. From our experience, up to 8 cores, the parallelization is achieved quite easily, but when we try to add more cores, we run into problems, which we'll describe now. So this is the first graph of our results. It's a graph of speed up with regard to the number of cores. And I don't know if you see the labels, but the most scalable one is the hybrid model, and it's not close to linear, which is the red dotted line. And the other models are, as you can see, are not scalable at all after 16 cores or even 8 cores. So it was pretty bad. We should keep in mind that it is not a typical Erlang use case, and usually the task with Erlang is to administrate, to manage or communicate some components, not to perform some computation using the most CPU power available. So we tried to monitor several different things, different approaches, and the tool that gave us the best results was LCNT. It's a tool that measures lock contention, and lock contention happens when a thread acquires some resource, and then another thread tries to acquire the same resource, but can't, and is suspended. And this tool measures the number of these collisions and presents the result.
So these are the results that we got after using this LCNT tool for our fine-grained model. On the left-hand side, I hope you can see the names of the locks that occurred most frequently. You also have the number of tries and the number of collisions that occurred, and how much time it took, and also appropriate percentage. And as you can see, the makeref lock was the most significant one in most of the runs. Makeref lock is a lock that comes up when you need a globally unique identifier, and you have to call the makeref function. The other locks are the time of day lock. This one occurs when you need to update time or set a timer. Run queue lock is connected to putting a process into a particular run queue of a scheduler. And a pix lock is a general lock of a process which protects several of its fields. So the makeref lock was the most harmful one for us. We realized that if we want to make the application scale, we have to get rid of it. So thanks to a lot of help from Lucas Larsson that we got, who's one of the developers behind the Erlang virtual machine, we managed to narrow down and locate which particular lines of code are responsible for this lock. And it turns out that we had quite a few gen server processes in our application. These are the arenas that I mentioned you about. And we used, to communicate with these arenas, agents used a function which is gen server call, which is supposed to be used for synchronous communication. And it turns out that this function depends heavily on the makeref function. So when we use this extensively, it turned out that the lock was also occurring very frequently. So we decided that we have to substitute it with the gen server cast. It's another function, but supposed to it's used mostly for asynchronous communication. Below you have the code, what what it looks like more or less after the change. And then we run the LCNT tool once again, and these are the results. As you can see, most of the other locks are still there. However, we managed to get rid of this makeref one, which is good. And another major enhancement that we introduced was to have a new logger. Before we had a logger that we have written ourselves, which didn't really perform very well, and we decided to substitute it with an open library called Exometer, which is available on GitHub. It's open. And we had quite a good experience with it, especially considering the feedback that we got from the developers behind it. And one of the main reasons that we chose this particular library is that we wanted to get rid of maybe not get rid of, but significantly reduce the time of day lock. Our previous logger depended on it extensively, and we were hoping that Exometer will improve the situation. And generally, we had a good experience with this tool. We had one major challenge. It was to monitor the fitness in the minimum fitness value in the system, because there is no global knowledge, as we said, and we have many agents all over the virtual machine, and we want to find the one with a minimum fitness value. So we had a few attempts for that. One was to use the built-in histogram entry in Exometer, which didn't work for us very well. So we decided to write one ourselves with the ETS tables, and this also didn't go very well. And we ended up using NIFs. And when we introduced NIFs, then the application finally started to scale somehow. So here on this chart, I hope you can see, you have on the y-axis you have the number of reproductions per second. This is just a performance measure. You can think of it as a number of algorithm iterations per second. And the orange line represents the algorithm performance after those two changes that I told you about. So the performance increased, and it finally started to scale.
So apart from these changes in all of the models, we also introduced one change specifically for the scale-based model. As you may know, the data, when you send a message in Erlang between processes, the data is copied in this message. And there is an exception for larger binaries. So Scale is creating a data processing stream, and uses a lot of processes, a lot of messages, so it's quite expensive. And we changed our representation of an agent from a list of floats to a binary, and it was a quite big improvement. So this is the graph of reproductions per second with regard to the number of cores, and the orange line is the version that uses binaries. And this is an only change that was switched between those these two models. So these are the final results. We can see that the coarse-grained model, hybrid model, is now close to linear, and the other models also improve significantly. We can notice that maybe the coarse-grained model was a better fit for our case. So to sum up, scaling Erlang vertically is quite not very easy. If you face a similar task in the future, you can try some of these tips. Most of them were explained earlier, but you should also keep your VM updated. The development behind the VM is ongoing, and we also observed an improvement just by switching the VM. If you're in trouble, you can also ask other people in the Erlang community, reach out to them. For example, on the Erlang IRC channel, we benefited from this a lot, so we recommend it, and we'll try to help if there is some need. We also open source this whole software, so if you would like to give it a try, it's on GitHub. Thank you.
Yeah, so this is a pretty detailed question, but why did you use GenServer cast instead of just sending a message to the GenServer?
Well, yeah, the arenas itself, there were gen servers, there were the behavior of gen servers. So we were either could send a message normally as with a bank in Erlang, or we could use a gen server cast, and gen server cast worked perfectly fine. So we got rid of this lock, so it was completely okay. Yeah, it's all right.
So why did you get a lock on time of day?
Oh, with the previous one, with the previous logger, you mean?
Yes.
Oh, so our previous logger worked. He had to check after almost every iteration. He had to call the function Erlang now, which uses the time of day lock, to check if it's an appropriate time to send a message to the logger. So it depended heavily on this, and yeah, and that's why the lock comes up very frequently. Yeah.
Any more questions? So thank you very much again.